Okay. So we have this, right? Now using this we can find, as we did it in the previous section, as E theta equal to J eta K I0 L e to the power of minus GPR by 8 pi r sin theta. H I is same except the theta term will not be. Is it okay? Is it okay? And if we go on calculating, we'll find that the radiation resistance for this antenna, what will be the directivity of this antenna? Can anyone tell me? What will be the directivity of this antenna? What will be the directivity of this antenna? The small dipole. What will be the directivity of this antenna? Can someone tell me? What will be the directivity of this antenna? Can you tell me what will be? Can you hear me? Are you there? Are you there? Can you hear me? Are you there? Can you hear me? Okay. Can you hear me? Okay. Okay. Yes, please rejoin, Rakesh. Please rejoin. Okay. So for others, what is the direct? What will be the directivity of this antenna? What will be the directivity of this? What will be the directivity of this antenna? See, it has the same sin theta pattern as the Hertzian dipole. Okay, so directivity will be same 1.5. Is it okay? Right? Okay. Radiation resistance is given by 20 pi square L by lambda square. So if what will be this? What will be this? What will be radiation resistance? What will be radiation resistance of the antenna? 7 point something. So that is 20 pi square 1 by 10 square by 20 pi square by 100. That is pi square by 5. What is this value? Yes, approximately 2. Will you check it once, Ritika? 1 point something, 1.8 or 1.9 something like that. Okay. So it is somewhat easier, like it was 0.3 ohms in the Hertzian dipole case, now it is 2 ohms. So it is larger but still very difficult to manage. Okay. So let us now consider the most general case. Okay. Where the antenna could be of any length. Finite length dipole. Okay. Now we drop any restriction on length. Okay, this is our dipole. This length is, the entire length is L. Okay. So one end is L by 2. And the current distribution is now IE x prime y prime z prime, that is equal to AZ I0 sine of k L by 2 by z prime or 0 z L by 2. This is equal to AZ I0 sine of k L by 2 z prime L by 2 z 0. Is it okay? So this will be the current distribution. Okay. So what will be the, we will use the same way. We will find A first. So A is equal to mu naught, sorry, not mu by 4 pi this. Okay. AZ minus L by 2 to 0 I0 sine of k L by 2 plus z prime e to the power of minus jkr by r dz prime plus AZ 0 to L by 2 I0 sine k L by minus z prime e to the power of jkr by r dz prime. Okay. Is it okay? So we do the same thing. Mu by 4 pi r rather small. So we now take the assumption that r for amplitude, r what is theta? What is theta? Let us see on this figure. This is my antenna. Okay. This is my coordinates z. Okay. This is y. This is x. This is my observation point P. This is my x, y, z. We consider this point here. This is x prime, y prime, z prime. X prime and y prime are 0. This is my r, and clearly this r, this is r minus z prime cos theta. Theta is this end. Does it match? Check. Check. Can we write this? Can we write this? Check. This distance is z. Can we write this? Once again, r equal to r for amplitude, magnitude is fine, but we cannot take r equal to r for phase, because once again this phase, it has got a k multiplied with it. Okay, that is why these two are different. Can we write this? Can we write this? Is it okay? Can we write this? Okay. So if we do this, let us once again take the r terms out because we are integrating in terms of z prime. So we can take the r terms out. Let us try with the a equal to mu naught. Sorry, not mu naught. So just give it mu I naught, mu I naught by 4 pi r a z or k. This is integral minus L by 2 to 0 sine of k L by 2 plus z prime e to the power of minus j z prime cos theta dz prime plus plus 0 to L by 2 sine of k L by 2 minus z prime e to the power of j z prime cos theta dz prime. Can we write this? Can we write this? Now see here something very interesting. Now see here something very interesting. This is a product of two terms. This term is called the element factor, and the other term, this term, it is called the array factor. Okay. This term, this is due to a very small portion of the current. This is due to a very small portion. This part is due to a very small portion of the antenna. Okay. And when we when we find the total field due to the entire antenna, we do this integration. Okay. Actually, it's not array factor. It should be space, not exactly an array. So this is the A due to a very small portion of the antenna. Okay. And how to find the total A? We have to integrate over the entire antenna. We have done this, right? So if we do this, then we will find that E theta, that is j eta. Once again, we focus only on the far fields. 4 pi r sin theta minus L by 2 to L by 2 i.e. x prime, y prime, z prime, dz. Okay, and h psi is same except the theta factor. Sin theta, of course. Sorry. Here there will be e to the power of plus j z prime cos theta z prime e to the power of j z prime cos theta dz prime. Okay, so these are my e theta and h psi. So the only thing what is remaining is this integration. How to integrate this? If we are able to find this integral, we can find the value. So the integral here, the value of this integral, we simply write it without doing the actual integration. This is cos of kl by 2 cos theta minus cos of kl by 2 by sin theta. If we do this integration, we will get this one. Okay. So e theta equal to j eta I0 to the power of minus jkr by 2 pi r cos of kl by 2 cos theta minus cos of kl by 2 by sin theta, and h psi is equal to j I0 to the power of minus jkr by 2 pi r cos of kl by 2 cos theta cos of kl by 2 sin theta. Okay, now we consider a special case. We consider a special case where L equal to lambda by 2 or the half wave dipole. Okay, half wave dipole. For it, if we simply put L equal to lambda by 2 in the other expressions, e theta equal to j eta I0 to the power of minus jkr by 2 pi r cos of pi by 2 cos theta by sin theta h psi okay. Can we write this? We simply put L equal to lambda by 2. L equal to lambda by 2, then KL equal to 2 pi by lambda into lambda by 2. Okay, and we get these expressions. Right? Is it okay? What will be WF? That will be half real part of E H E R E theta H psi, that is half eta I0 square by 8 pi square r square cos of pi by 2 cos theta by sin theta whole square. Right. So what is u? U will be theta I square 8 pi square cos of pi by 2 cos theta by sin theta square. D will be 4 pi u max by p dot. Okay, p dot will be theta I naught square 8 pi square cos cos theta sin theta. Okay, this comes around, this integral has a value I0 square by 8 pi c in 2 pi, where c in 2 pi that is equal to 2. So d will be 4 pi max by 2 dash 4 pi. What will be u max? This will be 4 pi by c by 2 pi, that is 4 pi 2 pi 1.64. Is it okay? Is it okay? You can see the derivation again. For half wave dipole, E theta equal to this and H high is equal to this. Alright. Now WF is half real part of E theta into H high conjugate. So we just put the value and we have found WF or the radiation intensity, okay, or sorry, or the radiated power density, okay. From there we can find the radiation intensity, that is R square, and the magnitude of WF, okay. So we get this value. Right. So P dat will be this. Is it okay? The detailed derivation is in Balanis, so you can check that. That the derivation is not so much important. What is important are these values, directivity, okay, the input impedance, and those things. So P dat is equal to eta I naught square 8 pi into 2.435, right? So radiation resistance will be what? Eta I naught square by 4 pi, sorry, radiation resistance will be half I naught square RR, that is eta I naught square 8 pi into 2.435. I naught square gets cancelled. RR will be eta by 4 pi 2.435. Eta is 120 pi for vacuum. 4 pi 2.435 30. So this is approximately 73 ohms. So the radiation resistance of a half-wave dipole is approximately 73 ohms. And without going to the derivation, Z in is 73 plus J 42.5 ohms. We do not derive this part. Any questions for this part? Any questions? Any questions? Anything? Want me to repeat? $42.5. Okay. So this is not, if you make the length a little bit less than lambda by 2, then the 42.5 is goes away and we have a perfect resistance. Okay. And this 73 ohms is very easy to match. Much easier to match with 50 ohms as compared to that 0.3 ohms or 2 ohms what we were getting. Okay. As a result, dipole antennas are very common. Even if we do not have this pandemic, you would have done experience with the half of dipole. It is there. Okay, we have plotted that sin theta radiation. Sorry, not sin theta, this is a bit. The pattern is this. For half wave dipole, the pattern is like this. Cos of cos. Okay. So in the next week we will start with loop antennas. So thank you. Okay, we will meet on Wednesday, one day. Okay. Thanks a lot.